Hello students, welcome to Saurav Sir's classes. The problem that we want to solve today says for n greater than equal to 1, let a n equal to n times 2 to the power minus n if n is odd and minus 3 to the power minus n if n is even. Now the sequence a n converges, a n mod to the power 1 by n converges, sum over n converges, sum over mod n converges are the various options. So we'll start solving the problem. Note that this is a multiple select problem and more than one options can be correct, so we have to analyze each option. Now what is sequence a n converges? What is a to n? A to n gives us n times minus 3 to the power minus 2n, which is equal to minus 3 by minus 1 by 3 to the power 2n. As n goes to infinity, this goes to 0, and a to n minus 1, this is equal to n times 2 to the power minus 2n minus 1. Now since we have n on the numerator and an exponential function on n in the denominator, this of course goes to 0 because this goes to infinity much faster than n, and so a to n and a to n minus 1 both go to 0, which means that a n converges to 0, and we can safely conclude that a is correct. The other things is sequence mod a n to the power 1 by n. So what is mod a n to the power 1 by n? This is equal to n to the 1 by n by 2 if n is odd, and 1 by 3 if n is even. Now this sequence, these two subsequences, let us see where these converge. The even subsequence a n to the power 1 by n converges to 1 by 3 because it's just the constant subsequence. The other thing, n to the power 1 by n, we know always converges to 1, which implies that this converges to half, and two subsequences converges to different constants, which say that sequence does not converge. If a sequence converges, all its subsequences have to converge and to the same limit. Thirdly, we have the series sum over n to 1 n equal 1 to infinity a n converge. Now how do we solve this problem? Now a series converges if the sum of its even terms and the sum of its odd terms both converge. The sum of even terms, sum over n even minus 3 to the power minus n, is less than equal to sum over n even 3 to the power minus n, which is equal to 1 plus 1 by 3 square plus 1 by 3 to the 4 and so on, which is just equal to 1 by 1 minus 3 square. 1 by 1 minus 1 by 3 square. And so the even terms, we see the series consisting of the even terms converge. Now what about the series n to the 2 to the power minus n if n is odd? So this gives us sum over n times 2 to the minus n odd. So this would be less than equal to sum over n to the power to the minus n all n, and let us see what this is. This is 2 to the minus 1 plus 2 to the minus 2 plus 3 2 to the power minus 3 and so on, which is equal to 2 to the minus 1 plus 2 to the minus 2, this plus 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 4, this plus 2 to the minus 3 plus 2 to the minus 4, this, and so on. So I'm just taking all terms from the beginning. Then since this is 2, we have the next term starting from 2 to the minus 2 and so on. If we sum this up, we have 2 to the minus 1 once, 2 to the minus 2 twice, 2 to the minus 3 thrice, 2 to the power minus 4 times, and so on. So this is just 2 to the minus 1 times this geometric series plus 2 to the minus 2 times this geometric series plus 2 cube times, and so on, which is just, now the sum of this geometric series is 1 by 1 minus half, which is equal to 2. So times 2 plus 2 to the minus 3 times 2, and so on, which is 1 plus 2 inverse plus 2 inverse square, and it is exactly the geometric series 1 by 1 plus half, that is 1 minus half, that is 2. So we see that both the subsequences, if we take the respective series, the odd series and the even series, both converge, and hence the entire series converges. Moreover, if we take mod an, then minus 3 to the power minus n becomes 3 to the power minus n, because n to the minus n, n times 2 to the power minus n will always be positive. We have already seen that mod 1 by 3 to the power n, this series itself converges, and so the series sum over mod an would also converge. So here A, C and D are correct and B is wrong. B was wrong because we saw that a n to the power 1 by n converged to different limits when we took the odd subsequence and the even subsequence. So this is the end of the problem. Now we will move on to the next problem. The next problem says let f from 0 comma infinity to r be defined like this: fx equal to x times e to the power minus x cube, e to the power 1 by x cube minus 1 plus 1 by x cube. Now the limit of x goes to infinity, fx, xfx and x square fx is all that we have to find. So for the first option we see limit x goes to infinity, fx equal to limit y goes to 0, x times e to the y cube minus 1 plus y cube by y we don't have an x here, sorry. This is after we take y equal to 1 by x. When x goes to infinity, y goes to 0. So we just replace all the 1 by x's by y's and x by 1 by y. So this is just limit y goes to 0, e to the power y cube minus 1 plus y cube by y. This is limit as y goes to 0. Since the above thing goes to 1 minus 1 plus 0, which is 0, and the bottom thing also goes to 0, we can apply L'Hopital's rule and differentiate the numerator and the denominator to get 1 below 3y square e to the power y cube plus 3y square, which is equal to 0. So limit x goes to infinity fx exists and is equal to 0. So A is correct. Now for B, limit x going to infinity fx, once again we do exactly the same thing. We put y equal to 1 by x and get limit y equal to 0, y cube minus 1 plus y cube by y square. This again by L'Hopital's rule is equal to 3y square e to the y cube plus 3y square by 2y. Now this goes to 0, the numerator and the denominator also goes to 0, but we can just cancel it out to get 3y by 2 e to the power y cube plus 3 by 2y. So this goes to 0 as y goes to 0, as both terms have y here, and so the limit exists and B is correct. Now for C, we again do the same thing. Limit x goes to infinity fx is equal to limit as y goes to 0 e to the y cube minus 1 plus y cube by y cube. So this, as y goes to 0, z also goes to 0 if we put z equal to y cube. So this limit is equal to e to the power z minus 1 plus z by z, which is equal to limit z goes to 0 e to the power z plus 1 by 1 by L'Hopital's rule, and hence this is equal to 1. So the limit as x goes to infinity fx times x square, this was x, this also exists, and C is hence correct. D says there exists m greater than 0 such that limit x goes to infinity x to the power m fx does not exist. Now limit x goes to infinity x to the m fx is just equal to limit y goes to 0 e to the y cube minus 1 plus y cube by y to the power m. So in the beginning, since this is equal to numerator goes to 0 and the denominator goes to 0, we can apply L'Hopital's rule once to get limit y goes to 0 m y to the power m minus 1 y cube 3y square e to the power y cube plus 3y square. Now since the numerator goes to 0 and the denominator again goes to 0, assuming m is greater than 3, what we'll do is we will cancel out the y square to get limit y goes to 0 3 e to the power y cube plus 3 by m times y to the power m minus 1 minus 2, which becomes m minus 3. So now another use of L'Hopital's rule. However, see that we cannot actually use L'Hopital's rule because the numerator is not going to 0 as y goes to 0, and this is not an indeterminate form. Rather, the numerator actually goes to 3 plus 3, which is 6, and the denominator has a y term as m is greater than 3, and so denominator goes to 0, which makes this entire thing going to infinity. So the limit does not exist if m greater than 3 limit does not exist, and so D is also correct. In this problem, all the 4 options are actually correct. If you have any doubts, please post in the comment section. If you like the video, please press the like button and subscribe our channel. Thank you.